Chemistry is often called the central science. It connects to so many other fields of study. One of the most fundamental concepts in chemistry is chemical bonding. It's all about how atoms join together to form molecules. Understanding chemical bonding is key to unlocking the secrets of the world around us. Why is chemical bonding so important for JEE aspirants? Because it forms the bedrock of chemistry. A strong grasp of bonding concepts is essential for tackling questions related to inorganic chemistry, organic chemistry, and even physical chemistry. In this guide, we will embark on an exciting journey through the fascinating world of chemical bonding. We'll cover the different types of bonds, their properties, and how they influence the behavior of molecules. We'll explore important theories like VSEPR and delve into the mysteries of resonance. Get ready to unravel the secrets of chemical bonding and ace your JEE exams. So fasten your seatbelts and let's dive into the captivating realm of chemical bonding. Ionic bonding is like a game of give and take, but in this game, electrons are the prizes. This fascinating process is fundamental to the chemistry that governs the world around us. Understanding ionic bonding helps us grasp how different substances are formed and why they have the properties they do. Atoms of certain elements really want to gain or lose electrons to achieve a stable electron configuration, just like the noble gases. Noble gases, such as helium, neon, and argon, are known for their stability because they have a full outer shell of electrons. Other elements strive to mimic this stable configuration by either shedding or acquiring electrons. This is where ionic bonding comes in. It's a type of chemical bond that involves the transfer of electrons from one atom to another, leading to the formation of ions. These ions then attract each other due to their opposite charges, creating a strong bond. Imagine an atom with one lonely electron in its outermost shell. This electron is like an extra piece that doesn't quite fit, making the atom unstable and eager to get rid of it. It desperately wants to get rid of it to achieve a stable state. By losing this electron, the atom can achieve a more stable, lower energy state, similar to the noble gases. Now picture another atom that's just one electron short of a full outer shell. This atom is in a state of electron deficiency and is actively seeking an electron to fill its outer shell and achieve stability. It's eagerly looking for an electron to complete its set. This atom is like a puzzle missing its final piece, and finding that piece will make it stable and complete. When these two atoms meet, it's like a match made in chemical heaven. The atom with the extra electron is more than happy to donate it, while the atom in need is ready to accept it. The atom with the extra electron happily donates it to the atom that needs it. This transfer of electrons is the essence of ionic bonding, leading to the formation of charged particles known as ions. This transfer of electrons creates ions, positively charged cations, the atom that lost an electron, and negatively charged anions, the atom that gained an electron. These ions are now electrically charged and ready to interact with each other. These oppositely charged ions attract each other like magnets, forming a strong electrostatic bond. This attraction is due to the fundamental principle that opposite charges attract, creating a stable ionic compound. This bond is what we call an ionic bond. It's a powerful force that holds the ions together in a structured arrangement, giving the compound its unique properties. Think of sodium chloride or table salt as a classic example. This common substance is formed through the ionic bonding of sodium and chlorine atoms. Sodium readily loses an electron to become Na+, a positively charged ion. This loss of an electron allows sodium to achieve a stable electron configuration, while chlorine gladly accepts it to become Cl, a negatively charged ion. By gaining an electron, chlorine also achieves a stable electron configuration. The resulting electrostatic attraction between Na+ and Cl forms the ionic bond in NaCl. This bond is what gives table salt its crystalline structure and many of its properties. Ionic compounds formed by ionic bonding are typically solid at room temperature. Their strong ionic bonds create a rigid and organized crystal lattice structure. They have high melting and boiling points due to the strong electrostatic forces holding the ions together. It takes a significant amount of energy to break these bonds and change the state of the compound, and are good conductors of electricity when dissolved in water or molten. This is because the ions are free to move and carry an electric current, making ionic compounds useful in various applications, from salt in our food to electrolytes in batteries. In the fascinating realm of chemical bonding, covalent bonding is all about sharing electrons between atoms. Unlike ionic bonding, where electrons are transferred from one atom to another, covalent bonding involves atoms sharing electrons to achieve a stable electron configuration. This fundamental difference is what makes covalent bonds unique and essential in the formation of many compounds. Imagine two atoms, each with an incomplete outer shell coming close to each other. They are like two puzzle pieces that fit together perfectly when they share their electrons. Instead of giving or taking electrons, they decide to share. This mutual sharing allows both atoms to fill their outer shells, achieving a more stable electronic arrangement. Each atom contributes one or more electrons to form shared pairs, which are then counted towards the outermost shells of both atoms. This sharing creates a strong bond that holds the atoms together. This sharing of electron pairs creates a covalent bond, holding the atoms together in a molecule. These bonds are the building blocks of countless substances that we encounter in our daily lives. Covalent bonds are like the glue that holds many of the molecules in our world together. They are responsible for the formation of a wide variety of compounds, from the simplest molecules to complex biological structures. Think of water, where each hydrogen atom shares an electron pair with the oxygen atom, forming two covalent bonds. This simple yet vital molecule is essential for all known forms of life. Or consider carbon dioxide, where the carbon atom shares two electron pairs with each of the two oxygen atoms, creating double covalent bonds. This molecule plays a crucial role in the Earth's carbon cycle and is a key component of the atmosphere. Covalent bonds can be polar or nonpolar depending on the electronegativity difference between the atoms involved. Electronegativity is a measure of an atom's ability to attract and hold on to electrons. Nonpolar covalent bonds involve equal sharing of electrons, resulting in a balanced distribution of electrical charge across the molecule. While polar covalent bonds result in an uneven distribution of electrons, creating partial charges on the atoms. This can lead to interesting properties, such as the ability of water to dissolve many substances. Covalent compounds, formed by covalent bonding, can be gases, liquids, or solids at room temperature, depending on the strength of the intermolecular forces between the molecules. These forces determine the physical properties of the substances, such as their melting and boiling points, solubility, and hardness. Understanding covalent bonding is crucial for scientists and researchers, as it helps them manipulate and create new materials with desired properties. From pharmaceuticals to new materials for technology, the principles of covalent bonding are applied in numerous fields. In the world of biology, covalent bonds are fundamental in the structure of DNA and proteins, which are essential for life. The double helix structure of DNA, for example, is held together by covalent bonds between the sugar and phosphate groups. As we continue to explore and understand the world of covalent bonding, we unlock the potential to innovate and improve our world in countless ways. Whether in the classroom or the lab, the study of covalent bonds is a gateway to understanding the molecular foundation of the universe. Section 4. Delving into the realm of metallic bonding. In this section, we will explore the fascinating world of metallic bonding, a fundamental concept in chemistry that explains the unique properties of metals. Metallic bonding is the special bond that holds all those shiny, conductive metals together. This type of bonding is what gives metals their distinctive characteristics, making them essential in various applications. It's like a giant electron party where the atoms share their outer electrons with all their neighbors. These shared electrons are not bound to any one atom, allowing them to move freely throughout the metal. Imagine a sea of electrons flowing freely around a lattice of positively charged metal ions. This sea is what holds the metal atoms together, creating a strong and flexible structure. This sea of electrons model helps explain many of the unique properties of metals. For instance, metals are typically shiny because the free electrons can absorb and re-emit light energy. The delocalized nature of the electrons in metallic bonding gives metals their characteristic electrical conductivity. These free electrons can move easily through the metal, allowing it to conduct electricity efficiently. When you apply a voltage across a metal wire, the electrons can easily flow through the sea of electrons, carrying the electrical current with them. This is why metals are such good conductors of electricity. This is why metals are used extensively in electrical wiring and appliances. Their ability to conduct electricity makes them indispensable in modern technology. Metallic bonding also explains why metals are malleable, meaning they can be hammered into sheets. This property is crucial in manufacturing and construction, where metals need to be shaped without breaking. and ductile, meaning they can be drawn into wires. This ductility allows metals to be stretched into long, thin wires without snapping. The sea of electrons acts like a cushion, allowing the metal ions to slide past each other without breaking the metallic bonds. This flexibility is what makes metals so versatile in various applications. The strength of metallic bonding varies depending on the metal. Different metals have different numbers of valence electrons and sizes of metal ions, which affect their bonding strength. Factors like the number of valence electrons and the size of the metal ions influence the strength of the bond and thus the melting and boiling points of metals. Metals with more valence electrons and smaller ions tend to have stronger bonds and higher melting points. Understanding metallic bonding is crucial for many fields, from materials science to engineering. It helps us design better materials and understand the behavior of metals in different environments. As we continue to innovate and develop new technologies, the principles of metallic bonding will remain fundamental. From the simplest tools to the most advanced machinery, metals and their unique properties will always play a vital role in our world. So the next time you see a shiny piece of metal or use an electrical device, remember the incredible science of metallic bonding that makes it all possible. This fascinating concept not only explains the properties of metals, but also opens the door to endless possibilities in science and technology. Section 5. Understanding Valence Bond Theory, or VBT. Valence Bond Theory is a powerful model that helps us understand how covalent bonds form. It's based on the idea that covalent bonds are formed by the overlap of atomic orbitals from two atoms, each containing one electron. Imagine two hydrogen atoms coming together. Each hydrogen atom has one electron in its 1s orbital. As they get closer, these orbitals begin to overlap, creating a region of high electron density between the two nuclei. This overlapping region represents the covalent bond. The two electrons, one from each hydrogen atom, are now shared in this bonding orbital, holding the two atoms together in a hydrogen molecule, or H2. VBT explains that the greater the overlap between the atomic orbitals, the stronger the bond. It also introduces the concept of sigma and pi bonds. Sigma bonds are formed by the direct, head-on overlap of atomic orbitals, while pi bonds are formed by the sideways overlap of p orbitals. VBT helps us understand the shapes of molecules. The geometry of a molecule is determined by the spatial arrangement of the bonding and non-bonding electron pairs around the central atom, as we'll explore further in the VSEPR theory section.